wasn't paying attention. I'm sorry for that. Okay, so here you have the conditional expectation. Okay, for the process at time t plus h minus j. Okay, given the past. Okay, so given the past of the process. Okay, that's the one. Okay, so you will explain these expressions, and of course j, the variable j can vary from 1 to p. Okay, so this is what it can be. So j can be equal to 1, 2, or something between 1 and p. All right? Okay, so this is how you would forecast an autoregressive process. Okay? And that is also basically put together for an autoregressive moving average process, and putting them together is quite difficult, but it's possible. Okay, so I will do this too. Remember the moving average processes. Okay, so this is how it works for a higher order autoregressive process. Okay, and for the moving average part. Okay, so this is going to be next example. So let's say you have a process and you have a moving average process of order q. Okay, so then basically this means that the process can be written as follows. So here you have the constant plus the noise, okay, and then plus b1 times the lag noise. Okay, so these past observations. Okay, so you have b2 times the noise at point t minus 2, and then plus blah blah blah, and the last one would be bq times the noise at point t minus q. Okay, so this is a moving average process. This is something you're not that familiar with. Okay, now here in this case you would basically do the same thing. So what would be the forecast of the process? So the forecast of the process at point t for time t plus h is going to be equal to the conditional expectation of these things. Okay, now the conditional expectation here, all right, so this is always been the case. Okay, so v plus the conditional expectation of the first one plus the conditional expectation of the second one plus the conditional expectation of the fourth one, and so forth. So you have the conditional expectation, okay, of the noise, okay, given the past of the process. Okay, so at point t plus h, given the past, okay, of the process. So you have yt, and then you have yt minus 1, and so forth. Okay, so that's going to be the conditional expectation of the first one. Okay, all right, so basically you would get for the same thing b1 times the conditional expectation of the noise. Okay, so at t plus h minus 1 given the past, okay, so given the past of the process, okay, and so forth, okay. And then you would have that this is, okay, this is going to be equal to bq, okay, times the conditional expectation of the noise, t plus h minus q, given the past of the process at yt. Okay, now here at this time you have to be careful, guys. Okay, I mean, of course, the expectations of the noise are 0, all right? And so are the conditional expectations. But provided that you take the conditional expectations of the future values, okay? So this thing, okay, this thing will be equal to 0, but only, okay, so this is equal to 0, but only if this value here is in the future, okay? You understand this? So basically, but only, okay, so if basically h minus 1 is greater than 0, okay, so the expectation of the noise are 0, but only if they are in the future. You understand? So the expectation of the future will be equal to 0, but not of the past, okay, because if you talk about the past, all right, then basically you would have that the expectation of the process will be the observation of the process. You understand? So the expectation of the future value is going to be equal to 0, but not the expectation of the past value, because the expectation of the past is equal to the observation of the process. You understand? Okay, so as soon as you have the noise, let's say, okay, you don't need to have the expectations anymore. Of course, the expectation of the noise would be equal to 0, but if you have the realization of the process, then the expectation is not 0. The expectation is the observation itself. Okay, so it's either 0, okay, so if, let's say, and then you have it here, so if h minus 1 is greater than 0, okay, so if h minus 1 is greater than 0, then of course the expectation of the noise will be equal to 0, but if it's not going to be 0, okay, so here in this case, it's going to be basically the observation of the process itself, okay, so this is what you observed, okay, in this case if h minus 1 is less than or equal to 0. You understand? So you have two different options, okay, so either it's 0 if it refers to the future value, or either the observation if it refers to basically the past of the process, because the past is already there, okay, so anything from, anything at time t or less is already known, okay, so you don't have the expectations anymore, because the expectation of a constant is already a constant itself. It's not 0, okay, you understand? Okay, so based on that, you can generalize the expectation as it follows. So this is going to be, and let me just, it's either 0, okay, or the observation itself. Let me just summarize this. Okay, so basically, you have that the forecast is either 0, okay, because if you refer to these future values of the process, then you already have that this is going to be 0. Okay, so it's going to be 0 if h minus q is greater than 0, guys. Okay, so if h minus q, this is the last one here. You see this here. This is the last one, h minus q. Okay, now if that is greater than 0, then the conditional expectations of the noises are going to be equal to 0, because all noises, okay, are basically from the future. Okay, sorry, I forgot the constant here, obviously. So the constant plus 0. Okay, so sorry about this. So here you have the constant. Okay, so the constant still is. Okay, because that is so the noise at point t minus h minus q is something in the future. Okay, and so are the others as well. Okay, so the future values, okay, or the expectations of the future values of the noise are going to be equal to 0. So this is going to be the forecast here. So this is going to be the constant if h minus q is less than 0, and if greater than 0. So if minus q is less or equal to 0, then it's going to be something else, because then you have the observations of the process. Okay. So if h minus q is less than or equal to 0, then you're going to get the observation itself. So this is going to be equal to, and then you have bh, okay, times the noise at point t, and then plus blah 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 blah. Okay, so the last one is going to be bq, okay, times epsilon t plus h minus q. That's going to be the last one if h minus q is less than or equal to 0. Okay, so then you're going to get basically the observations. I forgot the constant again. I'm sorry about this. Okay, so here you have the constant. Okay, so that's how it works. Okay, so the constant plus the corresponding observations. Okay, so because if h minus q is less than 0, then this is going to be, okay, something from the past. Okay, and which is already known. So if it's something from the past, then it's already known. It doesn't have an expectation anymore. It's a constant. And the expectation of the constant is going to be equal to the constant itself. Okay? It's not random anymore because it's already there. Okay? So this is how it will work for the moving average process. Okay? Good. All right. Now, that's going to be it here for this one. Okay, so this is how you would forecast an average, or let's say an autoregressive process and a moving average process, and you could, of course, you can put those together, so then this will you will get, okay, what you would have. Now, basically, okay, so this will be it, okay, and I'm gonna move on to the next chapter. Okay, so the next chapter will be about the estimation. Okay, so this is going to be chapter 5.2, and this will be about estimation. Okay. All right. Now, of course, you already know the arithmetic mean, right? Okay, so the arithmetic mean. And let's say you have y bar, it's going to be equal to 1 over t, capital T, times, okay, so then you have t is equal to 1 to capital T of yt. Okay, so basically you would take a sample, you sum it up, and you divide by the sample size. That's the arithmetic mean. Okay, I suppose that you are familiar with this. Okay, now this is basically an estimator. Okay, so this is an estimator. Okay, so for basically for the expectation of the process. Okay, so this could be the arithmetic mean is an estimator, and we're gonna summarize the asymptotic properties of that. So this is what you're gonna look at. Okay, so how you would estimate the expectation? Okay, just by the arithmetic mean, and suppose that we have a stationary autoregressive process. Now, what I would basically define here is the so-called long-run variance of the process. Okay, so before I go into this, okay, so this is going to be the next definition. Okay, so this is called the long-run variance. Okay, long-run variance. Okay, variance of a stochastic process. Okay. Process y. Okay, so suppose that we have the long run variance of a stochastic process, which you have to calculate. Again, this will be something that we need. Okay, so this is the variance in the long run, let's say. And I'm calling this omega squared. I'm not using sigma squared. I'm going to call this omega squared, so this is something else. Okay, because sigma squared was already used for the variance of the noise. Okay, maybe you remember. Okay, so I have to use a different letter. Now what you do is, you take the variance of the process, okay, and then you sum up the autocovariances. Okay, so the variance here, I mean, you have two processes. Okay, so the variance of the process plus 2 times the sum of all autocovariances. Okay, so here you start for the autocovariance at point H is equal to 1. Alright, so then here you have the autocovariances. Okay, so the autocovariance of the process H, yt and yt plus H. Okay, so that's how it goes. Okay, so this is the autocovariance. Okay, and basically H starts at 1. Okay, so you take all the autocovariances of the process, okay, which is not finite here in this case, so the sum here is not finite. You sum it up, okay, so that would be basically the limit, and then you multiply that by 2, and you add that to the variance, and this is going to be the long-run variance of the process. Okay, I will discuss certain properties, why we need this and whatever. Okay, so this will be crucial for stationary conditions. Okay, so when we look at stationarity or integrated processes. something will change regarding the long run variance of the process. So this is what we need to look at. Okay. Now, okay, so basic properties will, okay, so of the arithmetic mean is as follows. Okay, and this will be summarized in the next proposition. Okay. So, and suppose that you have a stationary autoregressive moving average process. So let's suppose, okay, so that basically y, okay, a autoregressive moving average process, okay, and which is stationary, okay, that is stationary. Maybe remember the stationarity condition for autoregressive moving average processes. So an autoregressive moving average process is stationary if and only if the autoregressive part is stationary. And the autoregressive part is stationary if the roots of the black polynomial have an absolute value which is greater than 1. Remember that? Okay, so that was the stationarity condition. Okay? Now, in that case, then we have the following. So then basically what we have is that the t times, okay, so t times the variance of the arithmetic mean. I'm not talking about the variance of the process, I'm talking about the variance of the arithmetic mean, will converge to the, or towards the long run variance of the process. Okay, so this is the long run variance, right? So this is the long run variance. Okay, so this is the asymptotic property of the process. If the process is stationary, then it converges to the long run variance. And of course, the long run variance will be as follows. Okay, so and in this case, the long run variance, okay, and this is what we're going to look at, is going to be equal to sigma squared. Now, sigma squared is the variance of the white noise, which is part of the autoregressive moving average process. Remember, okay, so sigma squared is the white noise. And then you have, basically, you have the lag polynomial b. Remember the lag polynomial at point 1 divided by the lag polynomial capital A. So the lag polynomial b was the lag polynomial of the moving average part. And the lag polynomial A was the lag polynomial of the autoregressive part. Remember that? Okay, I hope you still remember this. And then you take the square of that. Okay, so basically the lag polynomial. Okay, so maybe you don't understand it anymore. Okay, so leave a little space here because I wanna finish that here. I'm not done here yet. Okay, so if let's say if y is an autoregressive process of a moving average process of order p and q. Okay. So this means that what? So yt is equal to what? So here you have a constant, then you have a1 times yt minus 1 plus a2 minus, times yt minus 2 and so forth. Okay, so this is going to be the autoregressive part. Okay, yt minus p. And then you have the moving average part. So here you have the white noise, and then you have the lagged observations here of the noise. Okay, so b1 times epsilon t minus 1, blah blah blah, and so forth. So the last one is going to be epsilon, bq, okay, times epsilon t minus q. Okay, now maybe you remember this expression can be also denoted, okay, by using the following lag polynomials. Okay, so that's going to be similar. So here you have the lag polynomial, okay, times yt is equal to the constant plus the lag polynomial, okay, of the moving average part times epsilon. Okay, maybe remember this. You don't need to write it down because this is something that we already considered. Okay, but just for repeating what the lag polynomial was. Okay, so this is just a different representation. So the lag polynomial here is going to be equal to 1 minus a1 times L minus a2 times L squared, okay, and so forth, minus blah blah blah, minus a p times L to the power of p. I need a little more space. Okay, so AP times LP, so that was the lag polynomial of the autoregressive part, and the lag polynomial of the moving average part, okay, can be expressed as follows. So here you have 1 plus B1 times L plus B2 times L squared plus blah 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 plus BQ times L to the power of Q, okay, and L was, of course, capital L was the lag operator, okay. Now what I want to do here is I want to calculate the if you calculate the long run variance of the process and suppose that the process is stationary, then this is going to be the long run variance of the process, okay. So again, if you calculate the long run variance of the process, this is going to be it. So you have sigma squared times B1 divided by A1 to the power of 2. Okay? That's what you're going to get after you do this. It's not difficult at all. Okay? So, but this is just, this is just the long run variance. Okay? So this is what we do. And we also have furthermore, furthermore, we have another property. So that was the first one. So then T times the variance of the arithmetic mean converges to the long run variance of the process. And we have another property. So this is going to be the first property, okay? And the second property is, and based on that, I will develop some tests, okay? So then we have that T to the power of 0.5, okay? So this is the square root of T, okay? Times the arithmetic mean minus the expectation of the process. So here basically you have the expectation of the process, which is of course also the expectation of the arithmetic mean. This converges, okay, in distribution to the normal distribution. So this is going to be asymptotically normal with the mean 0 and the long run variance, okay, so not the variance of the process, the long run variance, because T times the variance of the arithmetic mean converges towards the long run variance of the process. So that's going to be the variance here of that. So based on that, okay, so based on that convergence criteria, you could develop tests regarding autoregressive processes, okay, or autoregressive moving average processes in general. Okay, so that will be the arithmetic that that we will look on to to develop test statistics and so forth. Okay, so this is what we're gonna do. Okay, now let's have a look at the long run variance of the process. Yes.
Sign on the arrow.
This is called the convergence and distribution. So this is D. Okay. So this means that this thing, okay, so this is asymptotically normal. Okay, so this, the interpretation here for that is, okay, so this thing, okay, converges towards the normal distribution. Okay? Okay, as of course, yes? Is that? So as of course okay, as of course T converges to infinity. Okay? And not just the normal distribution, but the normal distribution with the mean 0 and the long run variance sigma squared. Okay, so that would be the long run variance. So if I divide this expression by the long run variance, by the standard deviation, then this expression will be standard normal. You understand? Okay, so this is what the standardization is about. Okay, and of course, just to summarize that, so you have T to the power of 0.5, which is the square root of that. Okay, so times the arithmetic mean minus the expectation of the process. Okay, divided by the square root of the long run variance will be asymptotically standard normal. Okay? Right? So that's what I'm going to use to develop certain test statistics. Okay? So based on this convergence criteria. Okay? I have 10 minutes left, but I would just maybe give you a little idea how would you calculate the long run variance. Okay, so the long run variance of the process. Okay, it's also quite boring, so I want to skip, you know, 1 or 2 steps. But basically, okay, so let's say, I mean, you could do this for like, you know, whatever. You could calculate this for first order autoregressive model. Okay, so basically, I mean, let's say, just give you a little idea, okay, how it's done. Okay, so let's say, for instance, an example. Okay, so let's say you have, I mean, let's say first off you have a, okay, so you have an autoregressive process of order 1. Okay, so the first order autoregressive process, okay, which is stationary. Okay. Okay, so suppose n y is stationary. Then we had in the previous chapter, we had that the variance of the process, we have been calculating the variance of the process, was equal to sigma squared times 1 minus, it's times 1 over 1 minus a squared. And the covariance, okay, or the outer covariance of the process has been equal to a to the power of h times sigma squared times 1 minus 1 over a squared for h being greater than 0. Okay? This is something that we had in the previous chapter. Okay? Now, if you wish to calculate the long run variance of the process, okay? So the long run variance of the process is going to be equal to this is how you do it, okay? So basically you take the variance of the process and then you take 2 times the sum of all outer covariances, okay? So starting at h is equal to 1, so you take these. So h is equal to 1 to the and to plus infinity of the outer covariances, okay? So let me just give you a little idea what's going to be, okay? So if you take that, you plug it in, okay? So you could do this, maybe you could do this on your own as an exercise if you like. So then you have sigma squared times 1 over 1 minus a squared. This is going to be the variance. And then you have 2 times the sum of the outer covariances. Okay, so the sum of the, or the total sum of the outer covariances, let's say this is actually a nice expression, so you have a total sum. So from 1 to plus infinity. This is going to be the total sum of all outer covariances. Okay, so a to the power of h times sigma squared times 1 minus a to the a squared. Okay, now if you sum it up, you can see that this expression is also here. Okay, so basically this is how you would do it. Okay, but as you sum it up, so this refers to the geometric series, so I'm going to skip that because it's quite boring. Okay, so what you could find, okay, afterwards is going to be equal to 1 minus a squared times sigma squared. Okay, so all you need is basically the geometric series. I skipped that because it's boring. Okay, we've seen this quite a lot of times in other examples. Now 1 minus a, guys, is the lag polynomial at point 1. So this is going to be equal to 1 over the lag polynomial at point 1, and then you have the square of that, of course. Okay, so here you have the square of this times sigma squared. This is going to be the long run variance of an autoregressive, or the first order autoregressive process. Okay? Alright, so this is the long run variance of the first order autoregressive process. Okay, so here in this example. Now I'm going to take, basically I'm also going to take the long run variance, okay, of the moving average part. Okay, let's check that out too. Okay, so this is the long run variance of the first order autoregressive process. This is the representation for that. Okay, now what's going to be the long run variance of a moving average process? Now the moving average process is always stationary, so basically, I mean, this is quite clear. We already calculated the variance here of a first order moving average process. Now this was equal to 1 plus b squared times sigma squared. Okay, in the previous examples we have seen this, and the outer covariance okay, is either b squared, b times 0, sigma squared, or 0. Okay, so the autocovariance, and you have that here. Okay, so it's either b times sigma squared or 0. Okay, now when is this b times sigma squared? B times sigma squared if the time lag is equal to 1, and in all other cases, if it's greater than 1, it's greater than 1, not 0, as I said it, then it's going to be 0. Okay, so this was referred to as the finite memory, remember? Okay, so this was, the process has just a finite memory, the moving average part is just a finite memory. Okay, so the autocovariance is 0 after a certain point. Okay, that is also true for high order moving average processes, but in particular, I mean, this is the first order. Now, if you would take the long run variance, the formula is the same. So you have the variance of the process, okay, plus 2 times the sum of the, okay, so, or the total sum of all autocovariances, which is of course easier here, okay, because the autocovariances cancel out. They are all 0 after a certain point. So just for the first part, they are not 0, but after a certain point, they are. Okay, so this is the long run variance. Okay, so you only have the autocovariance for which h is equal to 1, because all others are going to be 0. Okay, so you can substitute here directly, and what you would basically get is that this is going to be equal to, and that's what you would have here. This is going to be equal to 1 plus 2 times b plus b squared. Okay, so here you have 2 times b here for that one, and this is going to be 1 plus 2 times b plus b squared times sigma squared. Okay, which is of course, and this is the lag polynomial of the process at point 1. Okay, so this is going to be the square. Okay, so this is going to be 1 plus b squared times sigma squared according to the binomial formula. Okay, so 1 plus 2 times b squared plus 2 times b plus b squared is going to be equal to 1 plus b squared, of course. Okay, and this is 1 plus b is the lag polynomial of the process at point 1. So this is going to be the lag polynomial, or the square of the lag polynomial, times sigma squared. Okay, so again, the autoregressive part, okay, just let me just summarize that. Okay, so if you put the two together, then it's going to be the same. Okay, so the autoregressive part had the lag polynomial that was equal to 1 over the square of the lag, had the long run variance, which is equal to 1 over the square of the lag polynomial at point 1 times sigma squared. The moving average part has a long run variance which is equal to the square of the lag polynomial at point 1 times sigma squared. And if you put the two together, okay, so then basically you would get the following. So if you, and this is not what I'm not going to finish here, but okay, so if you put the two together, so if you have an ARMA process, okay, so the first order autoregressive moving average process, then basically you would get that the long run variance, okay, so the long run variance of the process will be equal to b1 as b at point 1 divided by a at point 1 squared times the square of the variance, or the variance of the white noise. Okay, so if you put the two together, that's going to be it. Okay, no big deal. All right, so that's where it's coming from. Okay, and that's why it's basically the statement here regarding the longer variance is as is. I mean, you would have that there. Okay. Okay, guys. Okay, so I'm gonna finish here, and we'll continue tomorrow. Then, based on the corresponding convergence criteria, I will develop certain test statistics that you can use for hypothesis testing. Okay, so we stop here. Okay, see you tomorrow. Thanks a lot.